All right. Thanks, Randy, for having me again on this speaker series. What I'd like to talk about today is basically where we're at in the status of this ongoing research project that started nearly a decade ago, and kind of where we're at on the latest updates and findings that we've had with this. First off, we're talking about predicting tornadoes. It's tough. There's several different methods in which we use weather service wide to try to predict tornadogenesis. So I don't want this to come across as the end all be all. This is what we must use. This is just another tool that I want forecasters to have in the toolbox that they're able to use in warning operations. So I just want to make that clear that this is not what I'm trying to perceive as this is the end all be all. This is just another tool that we can utilize. So what are we talking about here? We're talking about a statistical model and a blended approach towards aiding forecasters during those warning operations and trying to increase lead time before tornadoes occur. So where did all this start? So this initiative started, like I said, nearly a decade ago with forecasters down at SBC in a research paper that was published by Thompson et al. In 2012. Basically, what they did is they looked at thousands of tornadic circulations from 2003 to 2011, and they assigned them whether their mesocyclones were weak, moderately strong, or strong. And they also delineated them based on the convective mode that they were. This took several years of intensive labor and analysis to get this data set started. But this is where the entire foundation for the project that I've worked on began back in 2012 with that paper being published. Then in 2015, the next research paper was published by Smith et al. Also at SBC, where they took that same data set and they assigned all of those tornadic storms. They assigned the probabilities of a particular EF rating scale based on the data set from 2009 to 2013. Again, this is conditioned upon that a tornado actually occurred, not predicting whether a tornado was going to occur, but one that was ongoing, estimating the associated wind speeds with that tornado. And this data set was further delineated into convective mode and STP for this research paper itself. So then the next step is they determined tornado probabilities on even a less conditional notion. This was from 2014 to 2015, and this incorporated even a more robust data set, including null set of severe storms that had low-level rotation, but not necessarily a tornado. Again, the remaining conditions that it had to be severe and rotating. And this was kind of the base of where the research project that I'm going to talk about today that we are still ongoing working with. But basically the characteristics of the circulation that they found was the peak low-level rotational velocity itself, the height, the circulation diameter, and then the more subjective portion of the analysis was whether or not the circulation itself was clear and tight, and then was there the presence of a TDS at the time they were doing the analysis. So then the next step, in 2018, Ariel Cohen and his dad, who was actually an economist for several decades, they took that data set and they determined a binary logistic regression model for tornado probabilities with a sample size of over 5,000 severe events. Over 1,000 of those were severe. And there's the equation with the various coefficients there on the bottom right. But basically that model outputs both tornado probabilities and wind speeds. And basically it's taking the blended approach of what Thompson et al. Had talked about with the various attributes of the circulation itself, and also applies an environmental parameter, STP, which I'll get into that here in a second, but basically trying to approach this from a blended approach standpoint where you're taking into account the characteristics of that couplet, as well as what is the environment actually capable of doing with that circulation. So considering from a background environment standpoint, as I mentioned, the environmental parameter that they decided to use was STP, which Thompson et al. In 2012 created that parameter itself. And basically they wanted, Ariel and his father and the other co-authors wanted to make sure that they're utilizing an environmental parameter that basically can tell us what is the environment capable of. If you're placing that circulation in that type of environment, you're getting those dynamic pressure perturbation structures, assuming that it's rotating. What is that environment capable of producing? Is it a tornado now, in 20 minutes, 15 minutes, so on and so forth? But trying to get that, to be able to anticipate when a tornado may occur on a reproducible nature like this probability model tries to entail. So from then on, Homer Baerg, who is at the University of Oklahoma, actually developed this fantastic web page that we actually use in warning ops at Topeka, and hopefully more folks will utilize it, even if it's just in a trial run, just to see how it actually works for you guys at your office. But there's the link at the top. But basically, you're putting in all of the characteristics of the circulation itself, along with that environmental parameter of the STP. The effective layer STP, I might add, not the fixed layer. So you input all of that data in there, and how we've utilized it at Topeka is this task has been done by a radar assistant, not necessarily the person who's actually issuing the warnings, but someone that's sitting at the PC next to the warning operations meteorologist. They're inputting this data scan by scan, assuming that we're in a tornadic environment, and they're getting the probability trends to that warning met that's sitting directly next to them. So you input all the data into that spreadsheet there, and it will output the various, the probability and the tornado wind speed estimations. But I don't necessarily want us to focus on purely the probabilities itself. And what Bill Gargan and myself have worked on over the past 2 years is how do these probabilities trend time preceding the time of tornado? And that's what I want to get into a little bit more. So this is one example of how the probability model you would utilize it in warning operations. So basically you identify that there's a circulation at ½ degree. You input the maximum rotational velocity within a 5-mile diameter. The maximum threshold that we have is that 5-mile diameter. Outside of the 5-mile radius, we don't consider that to be, that is excluded from being included in this probability model. Whether or not there's a TDS, as you can see in this example, in the low left, there is obviously a TDS ongoing in this radar scan. So while the simulated probability, simulated tornado probability is 97%, it actually is 100. But the estimated wind speeds from this were 125, when in actuality the observed damage assessment was 135. So it was pretty accurate overall. And this is a second example here. This is more of a line embedded supercell QLCS type event where the tornado probability is 5%. But again, you're looking for your maximum rotational velocity and the various characteristics that go along with that couplet itself. So in this case, the diameter of your maximum rotational velocity was 3 miles, and your height above radar level was roughly 3,100 feet, which produced a 5% tornado probability. But again, we're not, in this particular slide, we didn't show the environmental parameter, but it was taken into account for the probability itself. So some of the initial outputs from the probability model itself, they looked at 498 tornadic events and 499 non-tornadic events from that Thompson et al. 2012 data set. And basically you can see there is a decent distinguishable difference between tornadic events and non-tornadic events, roughly in the 15 to 20% time, or excuse me, 15 to 20% range, where you're transitioning from more of a non-tornadic event, non-tornadic circulation, to more of a potentially a tornadic situation, circulation. But what Bill Gargan and I really wanted to dive into is how do these probability trends evolve prior to a tornado actually occurring? So we wanted to go back in time and see how those evolved 30, 45, 60 minutes out, and see if there's any trends, and seeing how far back we actually see these trends go that could aid forecasters in getting advanced warning on tornado warnings itself. So our paper is actually just recently accepted within the Electronic Journal of Severe Storms Meteorology. And the actual title itself is Radar-Based Storm Scale Circulation and Tornado Probability Tendencies Preceding Tornadogenesis in Kansas and Nebraska. So we looked at 179 tornado cases in Kansas and Nebraska, and we calculated the tornado probabilities going back as far as we could identify at least some sort of circulation that was ongoing at half degree. When the half degree circulation was no longer obvious, that's when our analysis stopped for that particular event. So all in all, we analyzed 1,788 circulations, and that's taken us roughly 2 years to accomplish all of that. But on the right side, you can see the distribution of the various EF scale rating tornadoes that we sampled. So roughly 2/3, close to 2/3, were what we call weak tornadoes, EF0s, EF1s, and roughly 1/3 of those were SIGTORs that were EF2 or greater, EF2, EF3, EF4. So that's the base data that we used from that Thompson et al. Data set from 2012. So we wanted to dive into looking at the comparison between if we used a purely just radar-based, we're just looking at how the couplet trended. So this first one is looking at the trends of rotational velocity from those 179 cases that we looked at. So looking at the left side, that is the weak tornado scenarios that we looked at. There's not a lot of trends there. To say that you're going to issue a tornado warning 31 to 45 minutes in advance with great confidence that it's going to produce a tornado 31 to 45 minutes later is low. The same as if you're going to issue it 6 to 10 minutes earlier, your interquartile range is nearly the same at 6 to 10 minutes as it is 31 to 45 minutes. So using a purely radar-based rotational velocity trends as warning operations, you're not going to get a lot of lead time, especially on weak tornadoes. Now, there is a slight uptick when you look at the significant tornadoes on the right. You're looking at VROTs that they do trend upward as far back as maybe 16 to 20 minutes prior to tornadogenesis, but we're looking at just small incremental value increases at each timestamp, especially within 16 to 20 minutes prior to tornadogenesis. So, and that could fall, and I'll show an example here in a second, but that could fall in the error, the user error. I mean, we're talking 1, 2, 3, maybe 4 knots different in rotational velocity. That can easily be a user error in real-time ops. So again, while there is some trend in significant tornadoes, rotational velocity preceding when they produce a tornado, they're very minor and they're very modest. So it's hard to really get a lot of confidence that, yeah, we're actually seeing this uptick in rotational velocity that I have a lot of confidence issues tornado warning, going off a purely rotational velocity trend standpoint and not necessarily incorporating environmental parameters into your warning decision. So as I mentioned, this is one issue that you could fall into when you're purely using just radar-based analysis. So the top image there, your maximum velocity inbound is 15.5, maximum out is 24.3, your distance between is roughly 5 miles. So that gives you a rotational velocity of 19.9. Now, I don't necessarily remember what the SDP was on this particular event, but the tornado probability was 1. But remember, the rotational velocity was 19.9. If you simply just use a different pixel right in that same neighborhood, you can get a maximum in value of 24.3, maximum out value of 33, similar distance, but your rotational velocity is nearly 9 knots higher. And if you go back, if we went back to that rotational velocity trend plot, 9 knots is a huge difference between what we just sampled on the top versus what we sampled on the bottom. So that's what I was talking about as far as the user error. It could vary greatly based on which pixel you actually choose. And the corresponding tornado probability is only 2%. It went up 1%, even though you had a 9% or 9 knot difference in your actual rotational velocity itself. So that's why this blended approach could help and possibly aid forecasters in getting, the more trends, getting the better trends preceding tornadogenesis. So the second thing that we analyzed was looking at the circulation diameter. again, looking on the left side, the weak tornadoes, there's really not a huge signal. At least it's strong. There is a small signal, but it's not strong. Nothing that you would really have a lot of confidence, and that would aid you in getting a tornado warning out with additional lead time. Looking on the right side of this at the significant tornadoes, again, similar to the SIG tornadoes with rotational velocity, there is a trend upwards of 16 to 20 minutes out or so. But again, the values themselves are very small. They're not large. So having a difference in rotational velocity diameter between 1.3 and 1.9, that falls well within what a user could err in and accidentally maybe selecting the wrong value on the SRM itself. So while the last two images, they do show signs that they could aid possibly, the values themselves, the differences in the values are so small that I don't know exactly how well you could actually be aided in getting advanced lead time and tornado warnings. So what we're trying to get at is there's so many failure points when it comes to just using purely a radar-based analysis. Whether your radar beam actually samples the tornado, which that happens on a very rare occasion, and there's different methods on which you can actually get a tornado, whether it's a bona fide supercell, QLCS event, whether it's a land spot event. There's scenarios that this probability model isn't going to help also. A land spot event, it's not going to help you with that. Weak tor, which I'll get into here in a little bit, it's going to be tough for this probability model itself to actually aid every time in helping get advanced warning notice. This model just is not there yet. I'm not sure we'll get there, but it's not necessarily there right now. But like I said, the radar rarely ever samples a tornado, even when it's occurring. And the radar isn't necessarily sampling that vertical motion from those pressure perturbation structures that are formed because of that rotation, the surface vorticity that's being amplified that yields a tornadogenesis from a bottom-up standpoint. So we have to take this blended approach of using what is the environment capable of, along with what is our circulation telling us that's happening within that pressure perturbation structure, and how is that amplifying the near surface vorticity for tornadogenesis. So that's what the whole background motivation was for this model. And then Bill Gargan and I going back and seeing how these probabilities trended before the tornadoes were produced. So we're wanting to use this environmental data, this STP, to try to fill in the gap that radar doesn't tell us, that the radar only partially samples. We're talking about the circulation characteristics, the diameter, and the clarity. Is it an obvious circulation or not? When you take VROC combined with the environmental data, it can really aid, hopefully, in identifying that maybe a tornado is upcoming. And possibly offered a predictive signal, even on top of what we already utilize in the Weather Service. There's a lot of great tactics and techniques out there, but maybe this could also aid as another tool in the toolbox to help us get that additional lead time with tornado warnings. I'm not saying this probability model itself is going to aid us every single time, but if it can aid us just a few times to get even just a few minutes extra lead time. My wife is a nurse at a hospital, and I know if they need as much lead time as they can to get all their patients out of the rooms and into the hallways down to the lowest portion of the hospital that they can. So anything that we can do to try to aid in that is big. So like I said, I just want this to be another tool in the toolbox going forward. So what were some of the results that we found from our study that we did? So again, as I mentioned, there's not a huge trend in weak tornado probabilities. Again, it's aided by you're probably in a low STP environment where you're not going to have a big reflection in a strong rotational velocity. So you're not going to get these really high values of tornado probability. Again, maybe there's a decent trend 6 to 10 minutes out, but again, the values themselves are really small and the differences could fall within that error. So again, from a predictive standpoint, we're not necessarily going to be aided with this model in predicting those weak tornadoes. Now, on the other hand, looking at significant tornadoes, we may have a better signal possibly as far out as 16 to 20 minutes, where as you're crossing into that 25th percentile range in the 16 to 20 minute range prior to tornadogenesis, what we found is you're crossing roughly the 8 to 10% probability itself when you're crossing into that 25th percentile. And I don't necessarily want folks to focus solely on the values themselves, but more so just the trends over time. Because as we know, mesocyclones are not steady state. They're constantly changing. So unless even when we're in sales 3 and we're getting slight scans every 1 minute, there's still going to be changes in that half-degree rotation. And you are going to see fluctuations in the probabilities themselves. They may go up. You may be near the 50th percentile at 11 to 15 minutes. And then maybe you have something weird that happens with the mesocyclone 2 minutes later, and now you're closer to the 25th percentile once you get into the 6 to 10 minute time frame. Don't take that decrease as, oh, this tornado or this storm is not going to produce a tornado just because you have a decrease. You're still within the interquartile range of the 179 cases that we sampled that a tornado is probable in the next 6 to 10 minutes. So that's the biggest thing on this slide. I don't want you just to necessarily focus purely on the values themselves. Focus on the trends, focus on where it falls in line with the cases that we studied, and trying to get that predictive warning out. Hopefully a little bit more lead time than maybe what we already do. Again, we have to still, where there's additional work that needs to be done on this, but this is still kind of in the preliminary phase, but I just wanted to get this out there for now. So I wanted to do a weak tornado example to show how, again, as far as getting a lot of lead time with weak tours, it's just not going to happen. But we did have a successful event in Topeka. This was last September. Sarah, I think she's probably on the call. She remembers this day pretty well. I think it was her first tornado warning. But it was a unique case where we had purely a straight hodograph this day, and we were wondering whether or not storms were going to be able to move off of the boundary. But long story short, the initial time that we saw maybe the hints of some weak low-level rotation was roughly 6:41 p.m. and the tornado probability model was giving us a roughly 6% at that time. We were in a 1 to 2 STP environment, assuming that you had a right moving supercell that was ongoing. So, like I said, at 7:41 we had a 6% tornado probability. 3 minutes later, it had jumped to 10%. 2 minutes after that, it went down slightly to 8, but again, I don't want everyone to focus just on, oh, it's going up or down. Focus on the overall trends throughout more than just 2 minutes, because like I said, the mesocyclones, they're not steady state, they're constantly changing. But if you go 3 minutes later, then it jumped up to 15. So now we're in that 10 to 15% range where you're crossing that 25th percentile where, hey, 25% of tornadoes accompany this probability prior to them producing a tornado, somewhere in the 11 to 15, possibly 16 to 20 minutes prior to tornadogenesis. So then 3 minutes later, now it has a 24% probability. And at the time that we actually received a report of a tornado, the next day, we did not get this in real time, but it was the next day we got a report of damage. And it was at 7:54 p.m. is when they reported that they had the tornado impact them. So, and then going on past the time of the tornado, the probabilities stayed up, but then they eventually decreased, eventually going to 0. But what I want to focus on is the trends. So if you look on the left, starting the first scan that we got was roughly 14 minutes prior to the tornado being produced. So the probabilities themselves, the trends fall pretty good in line with what we found with our weak tornadoes, which this was a weak tornado. It produced a little bit of tree damage and a little bit of damage to a barn, I believe, but nothing substantial. So this was definitely a weak tornado. We knew that it was likely a weak tornado environment. So the probability trends themselves follow what we found fairly well. You compare this to the SIGTOR, it obviously does not fall in the SIGTOR environment, including looking at the trends from the cases that we studied. This just wasn't favorable for a significant tornado. Now I want to show a significant tornado, and this was not cherry picked. This was simply, I wanted to do a case that was not in Topeka CWA, just an event that I remember over the past couple of years. And I have removed the cities, the counties. So we just don't know where this tornado was. But basically, we're 30 minutes prior to the tornado. It doesn't look all that impressive on radar or velocity itself. So at this point, STP environment, I think, was a 4. So the tornado probability 30 minutes prior was 1%. 26 minutes prior, it's at 26%. 21 minutes, we're starting to get a slight increase as it looks like your outbounds are getting slightly stronger. You're up to 9%. So we're potentially crossing that 25th percentile range in that SIG-TOR environment where you may have a tornado produced in the next 16 to 20 minutes roughly. Now we're 17 minutes out. Now your inbounds are also starting to strengthen. We're up to 11%. We have a slight decrease as your outbounds, like I said, the mesos aren't necessarily steady state, so your outbounds decrease slightly, so that dropped your probability to 9%. You're still hovering near that 25th percentile range, however. And the other thing I wanted to talk about is we also maybe saw a weak sinusoidal pattern, and this may be due to as supercells cycle, their low-level mesocyclones cycle. That may also be why we see these increases and decreases in probability, because it's reflecting as that supercell is cycling. And I think that's what we saw with this case here. So again, this is 12 minutes prior to tornadogenesis. We're at 9% tornado probability. 7 minutes, now we're jumping up into more so the 50th percentile with probabilities themselves at 25%. We're still nearing the 25% range. And again, we're 3 minutes prior to tornadogenesis. And then 2 minutes after, we have a strong couplet, we have a TDS. So obviously the tornado probability is 100%. But I wanted to focus on the trends themselves. So this is, obviously we knew that if there was going to be a tornado, it was likely going to be a SIG-TOR. So I wanted to compare how the trends were in comparison to the cases that we had. So looking back to the 30 minutes prior to the tornado, again, this doesn't necessarily fall right in the middle, right near the 50th percentile for probabilities leading up to tornado. But looking at the overall trends, there largely was an uptick in probabilities, especially as you got, closer to 20 minutes. Yeah, we did have that one deviation roughly about 13 minutes out. But again, we're not talking about mesocyclones being steady state. There can be cycling that could affect the probabilities themselves. But just know, this should hopefully just aids forecasters in knowing, hey, this thing really is capable of producing a tornado. We really need to keep our eye on it and focus maybe on this one storm. But overall, it behaved fairly well in comparison to the other cases that we looked at. But yeah. So the conclusions that I wanted to make, again, this is not meant to be the end-all be-all. It's just another tool in the toolbox to help us with the difficult task of trying to identify tornadogenesis with increased lead time. The conventional radar, it can, but it doesn't offer a lot as far as trends prior to 15 minutes before a tornado occurs. You can get more lead time with a stronger tornado environment due to you're likely going to have a stronger rotational velocity, and you're also going to be in a stronger STP environment. Again, not all tornadoes are the same. There's going to be differences. There's going to be fluctuations in the probability that will result in differences in lead time that this probability model can give you. But overall, it can give you those trends, hopefully preceding the time that it produces a tornado. So VROT trends, they're modest, especially for weak tornadoes. Same with the probability model. They're very modest. And it only becomes apparent maybe 5 minutes prior to a tornado for a weak tornado itself, maybe a little bit more for SIG-TORs. But utilizing the blended approach and utilizing that in your warning operations with the other methods that you use, maybe you could get more lead time. There could be a stronger signal, maybe out as far out as 20 minutes. And that could even be magnified slightly longer for the SIG-TORs. Like I mentioned, this isn't going to necessarily help you with every weak TOR scenario. It's not going to, because you're going to have a weaker STP environment that's going to yield weaker rotational velocities. It's just going to be tougher to get increased lead time utilizing this probability model. So where are we going forward. The next step is we're gonna try to get a null data set that's just nearly the same size as our data set that we currently have, close to 180 cases. That way we can compare how do null cases and their tornado probability trends compare to both weak and significant tornadoes. That way that could hopefully further aid us in confidence for issuing tornado warnings and increase the usefulness that we can have in operations. So finally, I just want to say a huge thanks to all of the co-authors that were on this paper itself. Bill Gargan, who's also at our office in Topeka, Ariel Cohen, who's currently the SUE at Miami, but will be moving to Pueblo very soon. Rich Thompson and Brian Smith, both of SPC, Alan Girard, Severe Storms Lab, Chauncey Schultz, who is the SUE at Bismarck, and then Larry Kelly and Heather Nepal, both forecasters at the National Weather Service in Miami. I want a huge thanks to those. They definitely helped us get this across the finish line. While we're not completely across the finish line this step, we are across the finish line, and we'll be working on additional work in the months and years to come. So with that, I'd like to thank everyone who joined on the call today, and if you have any questions, please let me know.